Today, this morning, it's Jeff Schenker from Michigan, which is going to tell us about dissipative transport in the localization regime.
All right, thank you. It's very nice to be here. It's a great workshop, so thanks to the organizers for organizing this. It's always nice to come to Cambridge. So I'm going to talk about joint work with Jörg Froelich. Make sure I don't forget to mention my collaborator. And the problem, well, let me describe what it is that we wanted to understand and what the status of the project is. So the basic context is a model that's, of course, very familiar to all of us in the room, or at least many of us, which is the Anderson model. So let me write that down. And for simplicity, I will simply always take the initial condition to be a delta function at the origin, just to avoid having to carry it around in formulas, although obviously that's not terribly necessary. And this is, of course, taking place on L2 of ZD, so tight binding model. And the operator H omega is the usual nearest neighbor hopping plus random potential. And of course, it's very well known that under suitable assumptions on the random potential here, say maybe they're independent, identically distributed with a nice enough density, that if U over lambda is sufficiently small, some parameter, which I've labeled kappa sub A for Anderson, then we actually have exponential localization. So for instance, solutions to the above equation are exponentially bounded in that form. Yeah, with some positive mu. Okay, so this is the phenomenon of Anderson localization, and of course it was a surprise of sorts in theoretical physics when it first was understood that, in fact, the disorder could be responsible for completely eliminating transport in this wave equation. And, but of course now it's very well understood in mathematics, and I don't need to tell you that because some of the main players in that field are in the room. So now, of course, this model is a cartoon of sorts. It's at best an idealization, and real systems have various properties which mean that there always is some sort of transport present, and you may want to understand in this strongly disordered regime what kind of transport can happen. So the particles that are described by the Anderson model on their own can't propagate according to the wave equation, but of course they're always at least weakly interacting with something out there in the universe, and you might want to understand how that how transport can be induced by their interaction with something else. This also, of course, is a venerable subject in physics. Mott in the 1960s analyzed exactly this problem, and in fact wrote a formula for the conductivity in this localized regime. And I'm not specifically going to talk about that formula or that approach, but I just want to mention that I'm of course aware that other people have thought about this before. So the picture that I want to have in mind is, here's my ZD, and I have my quantum particle, which is not hopping very much around on here, right? It's trapped, exponentially localized, but there's some thermal reservoir which it's interacting with. R stands for reservoir, not for rain, even though the picture sort of looks like I guess it would. So there can be an exchange of energy here, and the reservoir can absorb or kick energy back into the system, and it can cause the particle to be kicked from site to site. And of course, actually writing down this problem is, well, writing it down is easy, but saying something actual about the problem here is somewhat difficult. We should consider the space L2 of ZD tensor some Hilbert space for the reservoir, and we should write down a Hamiltonian for the joint system, which will include the Anderson model, tensor the identity, plus some Hamiltonian for the reservoir, plus some interaction term, and we might want to consider the long-time dynamics of that problem. Now that is not the problem I'm going to talk about. There's a sort of well-accepted approximation in physics that's interesting to look at, which is a Markov approximation, which it comes about through a weak coupling limit on the interaction with the reservoir. And so we're going to reduce this. So we're going to take this limit just formally. In fact, I'm not actually going to write down anything on the joint system. I'm just going to write down the limit equation. So you make this Markov approximation. So this is a weak coupling limit. And you reduce it to an equation back on L2 of ZD. But not for the wave function anymore, in fact, for the density matrix. So this is, well, let me just simply write down the problem so that we can get to some math. So, of course, there's going to be another term here. So the density matrix here is going to be a trace class operator on ZD, positive trace class operator with trace 1. Which, of course, if I was merely considering the wave function, would just be the rank 1 projection onto the wave function, if that's a pure state. But let's put a coupling constant there. So the Markov approximation leads to an equation like this, where L is, at this time, just simply a linear operator that's defined on this space, which has certain properties. And it accounts for the effect of this interaction with the system, at least in this weak coupling limit. And so we can ask about transport properties for this equation. And that's, in fact, what I'm going to do under suitable assumptions of L on L, is understand the transport properties of this equation. This L is not a commutator, no. This is a commutator, yes. This is so I mean, what you want to think is that rho t is something like projection onto psi t. So it's psi t, psi t and inner product with psi t. And when you take the derivative of that, you pull out exactly this commutator. So this is the
Rho 0 is still delta 0.
well, rho 0 is now going to be delta 0. Well,
Yeah.
I guess, I should pick a notation. If I'm going to use Dirac notation, then that would be the way to write it. Okay, so I should tell you something about what this L is. And so I'm not going to describe to you the process of getting L from a formal calculation, but let me just say some properties of L. So, but of course, the main point is that even if I consider a pure state here, that when I take the partial trace onto this, and get rid of the reservoir, that I no longer have a pure state. I no longer have a vector state on my Hilbert space. And thus, I'm sort of forced in dealing with the open quantum system of this sort to deal with the density matrix. But in this weak coupling limit, I can get an equation that closes for the density matrix on its own. And but it's no longer this. It's no longer the Schrodinger equation for the wave function. It's this more general thing. And the key thing here for those, I mean, well, the exponential of this L stands for Lindblad, by the way, is a completely positive, is a semigroup of completely positive maps. Okay, and completely positive, you can basically think of it as preserving the positivity property of density matrices, but you actually have to also preserve positivity on all tensor products. And this is a particular class of maps which is well understood, and the general theory of these things goes back to the 70s. Okay. What's that?
L is bounded.
L is bounded in this case, yes. L is a bounded generator. Yeah.
So you're not going to tell us, this is just motivation.
This is all motivation. I'm just going to write down an L ultimately. Yeah.
And you're not going to tell us how lambda and G are related? I mean, what kind of scaling limit?
Once I have, I'm not going to tell you how, okay, so G is not related to lambda at all. G is related to something I didn't even write down, which was the coupling between my Anderson model and some heat bath.
Yeah, but that disappears in the limit, right?
That disappears in the limit,
So
yes.
G must come up. I mean, you must do some scaling limit, which
It doesn't
G is
disappear.
effective.
Yes.
Huh?
You have to rescale the time.
You rescale time and you rescale, so
Time is roughly speaking G
Okay.
squared times all time.
I wondered about doing this part of the talk at all.
No,
I
don't
thought
do
about
it,
simply,
Don't do it. Just tell me I should read the papers from the 70s. That's fine. I just
Yes.
wanted to know if there's a simple relation here that you can point out. If not, then
you rescaled it between G, well, I mean, of course, G is sort of fictitious because I haven't told you what L is, and the only reason I put G there is I want to now take a small G limit later. And so, basically read the paper, yes. so, no, okay, or do it yourself, right? Write down this big system, and
yeah, but you haven't told me what the big system is and what
Well-
scaling. I thought G is maybe an effective lambda or something, but
no,
isn't
G
that-
is, right, so I should have done that. So take H omega tensor the identity,
Ah,
plus
so G is
the
coming
identity
from the
tensor
coupling of the heat bath.
Exactly.
plus G,
Over limit.
and take the Van Hove limit, exactly.
And lambda is you fix
Lambda's my fixed disorder. In fact, I want lambda to be large at the end. It's not essential for everything I'm going to say,
So
but
lambda is still in there. Sorry, I
Right.
missed this point. Yeah, that's
Right.
the heat bath coupling. Okay, sorry.
okay.
Yeah.
And this G is not the same as that G because there's been a rescaling that's been taken.
I got it.
Okay, good. Okay, so now if you really honestly look at this problem, then you should do something rather complicated because you really, when you do this Van Hove limit, you can write down a kind of diagrammatic perturbation theory. You have to compute the contribution from certain diagrams. You get the Van Hove limit by taking only the ladder diagrams for the interaction, and you get something rather complicated because of the random potential. And I'm not actually sure how to deal with that system exactly.
Davis result for the fly direct.
What's that?
Davis result from 70s would work.
Yeah, no, that in terms of the existence of it, would it?
Before. You would have it, is it just condition probability per unit time?
Well, on the spectrum, right. You would get a jump, essentially a jump process on the spectrum of the random Schrodinger operator. Yes, right.
And that rigorous.
That's, yes, but I'm going to look at something even simpler than that, which is let's just look at this equation. Let's look at an equation of this form. And let's suppose that L, so the thing you would get if you did that, of course, is stochastic. L would depend upon the disorder because it's explicitly written down. The explicit representation for it is essentially as the generator of a jump process on the spectrum of H omega, which is why I say it looks rather complicated. So I want to suppose that the L that I get is fixed. It's non-stochastic. And commutes with translations. Okay, so I mean, this could have just been the starting point. I could write down the equation and say, let's just analyze equations of this form. Okay. So, and in fact, I'm going to take an slightly more restrictive version of this L. So let me now define the Lindblad generator that I'm going to look at. I'm going to introduce some notation here, which involves wanting to take the Wigner transform of my density matrix. So I will use a capital X to so I'm going to sort of use a hybrid notation here. Whenever I use Dirac notation, I'm going to refer to Bras and Ketz related to the positions of sites in ZD. And I'm introducing some auxiliary variables, which are basically the X is the sum, so kind of the center of mass, although I haven't divided by 2, of the two sites that sit there, and C is their difference. Okay? And these guys are subject to a constraint, which is that they should be, their sum should be an element of 2 times CD, since, well, that's just because we're working the type binding approximation, we're forced to deal with that. Okay, so, and I'm going to, the form I'm going to take for my Lindblad operator is as a difference of 2 terms, a gain term and a loss term. The gain term is given by the following expression. And I'll explain, I'll motivate what this is. And the loss term is essentially determined by the gain term by the requirements that I've written down, or that I mentioned, sorry, for the Lindblad operator. But let me write it down explicitly. So you can get some idea of why it has to be this way, because you can see that the trace of the density matrix should be conserved by the Lindblad operator, which in other words, the trace of the Lindblad operator applied to a density matrix should give you 0. And that's where part of where that comes from. Okay, so what is this? If I introduce the, so my terminology here is that R is I will call this the gain kernel. And if I introduce the Wigner transform of rho, which is the Fourier transform of what I wrote up there with respect to the variable xi, then then you can check that the Lindblad operator is given by the following expression. Integration over the d torus. So P naturally lives in the torus 0, 2 pi to the d. And let's see here. Get this right. Integrating with respect to Q in this expression. Okay, so here, R hat is a non-negative Borel measure on the torus, which we can think of actually as the jump kernel for a Markov process on the torus. Now, the torus here is the space of the quasi-momenta associated with particle hopping on the lattice. So what we have here is simply the Lindblad generator is something related to a Markov process on the momentum space. So what's happening, what this model is describing, is one in which we have propagation with respect to the random Schrodinger operator, but at exponential times, the particle receives a kick and its momentum is is altered according to this jump process. Okay, so
And this is symmetric, the R hat in P and Q, or?
well, so you can ask whether it should be symmetric. Actually, in general, they don't end up being symmetric, but I do need something close to symmetry here. So now, if you see, the thing is, if you do this with lambda equals 0, and you really take the Van Hove limit, and you see what you actually get something that isn't symmetric. In fact, it satisfies detailed balance at the temperature of the heat bath. I can't deal with those Lindblad operators. In fact, I need to know that this Lindblad, I don't need symmetry, but I do need to know that so I should put a hat over this because it's acting on the Fourier transform. So I do need to know that the uniform, that Haar measure on the torus is the invariant measure for this guy, which would follow from symmetry, but actually formally you don't need symmetry to get that. So let me see here, maybe. So let me write down the assumptions on my on R. So, well, the first thing I shouldn't even really necessarily mention, which is just basic to the model, I mentioned this whole business of the even elements. So the jump kernel has to have the property that it vanishes if you're trying to see. The particular lattice that eta lives in depends upon the lattice that x lives in, and so but the differences always have to be these even things. I already mentioned the non-negativity, so this guy is a non-negative Borel measure. It's in general not absolutely continuous with respect to Haar measure, actually. It's very, one wants to be able to consider things which are delta functions, basically hopping on maybe energy shells. Okay, which translates, if you like, to arc C eta as a function of positive type, because they're related by Fourier transform. So the condition that I said before about the L1, I need this particular condition, that is equal to 0, which translates to not symmetry, but symmetry if I integrate out, if I take the marginals, like this. Okay, so I don't need full symmetry, I just need this relation. Okay. So if you like, a sufficient condition for this would be just to assume that it's a symmetric jump kernel. And then finally, the other thing is that I need a spectral gap condition. Okay, so, and these are integrals over both variables, so I'll put, just to emphasize that. Okay, so this condition tells me that the constant function of the torus is annihilated by the Lindbladian. Basically what this condition is telling me is that everything else, nothing else is, and in fact uniformly so. So this is a spectral gap condition on the Lindbladian, and it tells you something about the exponential return to equilibrium for the jump process that's described by that equation, that it actually returns to equilibrium exponentially on timescales that are driven with a mass driven by c. Okay, and actually, well, I guess there's one other technical condition which is related to boundedness, which I won't bother to write down. So basically, I mean, if you think about all the possible measures you could write down, then they might or might not generate a bounded operator, but actually what I would like is for this to be a bounded operator on L2, which allows actually even for singular things where the kernel itself is a singular measure. But, okay, so good. And the other thing is symmetries. All right, so I think I can safely erase that. Erase Jörg's name now too. You all know who he is. Okay. So for simplicity, let's assume symmetry under inversion and lattice rotation. Okay, so in what I wrote down, formally R could have different behavior in different directions. Just to get a simple formula, I want to assume that
The Hamiltonian is invariant with respect to that.
well, the Hamiltonian already was, because I said, but I mean this.
It is random.
Well,
It
right,
could be
no.
varied in the probability, not
For- right.
rotation.
This is for R. I mean for R hat here. Okay, for R, right? Okay. So permute coordinates and you get the same value. Invert coordinates and you get the same value.
Characterizes somehow your interaction with the reservoir.
Yes, right. So I mean, I said suppose it commutes with translations, and what I really mean is it's commuting with sort of the full group of symmetries under distribution of the random Schrodinger operator. Right. So, and let's let rho t solve the equation, which is already here. So I'll write here SE for Schrodinger equation. So let's let this solve the Schrodinger equation again with that initial condition for simplicity, and let's let G be positive, and R is above. Then the diffusion matrix, which is the limit of position moments, exists. And satisfies, first of all, by the symmetry that I imposed because of the asymmetry under inversions. It's actually diagonal, and it's a multiple of the identity. And this diffusion constant is finite and positive. Okay? Now, that's probably not going to come as a surprise. Informally, simply what's going on is that the particle's getting kicked at periodic times with this Markov process, and it's generating a random walk. What is more interesting, although of course proving it requires some effort, although not terribly much, if U over lambda is small enough, as I defined before, below the Anderson transition. So I have the Anderson localization condition, which I erased, unfortunately. But well, then this diffusion constant, which depends upon G, is linear in G for small g, and that constant is positive and finite. So the localized system interacting with the heat bath does in fact diffuse, but it does so extremely slowly and in a way that we can control quantitatively. That the interaction with the heat bath causes a linear growth of the diffusion constant for small g. Okay. So this equation is really the main point, although it is interesting to see that we have diffusion up here. Now, it's another point that I should make is that in fact in all of this, this result uses localization and uses, of course, then the fact that I'm looking at a random Schrodinger operator. In fact, it only uses it through this estimate. I need nothing else. So well, not quite nothing else. But this result actually doesn't require much of the structure of random Schrodinger operators. I don't need to know that the potential is random. In fact, this would hold also for any quasi-periodic problem we would write down, in fact, for any ergodic spectral problem, so appropriate for this conference, that you might write down. Okay, so as long as your potential is given by the evaluation of some function at shifts on some auxiliary probability space, so it could even be a periodic potential, in fact, then this result would hold. Okay. Although, obviously the proof might need to be modified a little bit actually for periodic so the positivity and finiteness of the diffusion constant. However, getting this estimate depends very strongly on having localization for the system in the exponential form that I wrote it down before.
And if you have no potential?
If you have no potential, then the diffusion constant, so if lambda is equal to 0, the diffusion constant is constant over G. And actually, it's even much simpler for that. But not the same constant, of course. Okay, good.
For periodic, you get it to blow up as G goes to 0 as well.
It would blow up like 1 over G as G goes to 0. Honestly, I haven't done the calculations for periodic, but that should, and it's not going to be included in the paper, but it's a calculation which one ought to be able to do. It's by exactly the same method. In this case, it really is equal to a constant over G. But for periodic, it wouldn't be so simple, but it would blow up like 1 over G. Okay, so what I want to do now is give you some notion of the proof. Okay. So the fact that the off-diagonal elements vanish and that the matrix is multiple of the diagonal is actually easy to see because of the symmetries. In fact, it already holds at all fixed finite times for this equation by the symmetries, for this quantity, sorry, without taking the limit. So the fact that it's a multiple of the diagonal, that it's a multiple of the identity, we know. So basically, we can simply look at one of the position moments, and let me move over to the other coordinates that I had written down. So we can look at this, where I just take the first coordinate of x. And it suffices to prove that this converges to some number, which will be that d. Okay. And there's a factor of 2, which turns into a factor of 4, if you want to be honest here, because capital X is the sum of 2 coordinates. So So if I want to really get to that, then I have to divide by 4. Okay. So now I'm going to think of rho t as a function of the coordinates x and c that I wrote down, but also the disordered environment. Okay, and I'm going to think of this guy as an element of, well, okay, so naturally the density matrix is a trace class operator, but who doesn't want to work in a Hilbert space? So we're going to think of this guy as a Hilbert-Schmidt operator, which it actually is at all times because of general bounds on the propagation here. So it actually has, for any fixed finite time, exponentially decaying matrix elements because of the initial condition I chose, and so it's actually also in the Hilbert-Schmidt ideal. So, so I can write it as a Hilbert-Schmidt operator, as a random Hilbert-Schmidt operator. So I'm going to think of it in this space, which is a nice Hilbert space. Okay, and I'm going to introduce some translations of things on this space, which are translations. So S is a translation of the actual, it's an actual symmetry of the problem. So I'm going to translate the coordinates, the spatial coordinates, and the disorder. And the way that that is done, I'm going to shift x shifts by 2. If I move both the left and the right coordinates of the density matrix, then their sum shifts by 2. The difference does not shift at all, and the disorder is shifted by like that. Okay. And the minus signs are there for the standard reason that if you want the shift to represent a shift in a particular direction, then formally you need to move other things backwards. So the argument's backwards. So this really picks up the system and the function psi and moves them in space. Okay. So, and of course, this translation of the disorder coordinate is at a point x in ZD is just that. So omega was defined before to be this function by this random function. But as you can see, all I really need is, for this, is some implementation of translations on this space. So really just the setting of ergodic operator theory. Okay, so now the point is that this is an honest symmetry of my problem if I consider the problem on this augmented Hilbert space, which includes the disorder coordinates. In other words, it actually commutes with the generator. And so a natural next step is to take a Fourier transform. So we're going to define for an element of this Hilbert space psi hat k. I'm going to think of k, which is my Fourier variable, as a parameter, so I'm going to put it as a subscript there. And what should I do? I should act on my function. So psi is ultimately going to be the density matrix, but I just want to be considering an arbitrary element of this space. I hope that's sort of clear from the discussion. And I'm going to translate it according to that. And where will I evaluate it? Well, I need to evaluate the first coordinate somewhere and get rid of it. I'd like to sort of evaluate it at the origin, but I may or may not be allowed to evaluate it at the origin, because remember, because of the lattice structure, x and c have a constraint on them that their sum has to be an element of the even multiple of 2 of ZD. So I need to plug in something here. I need to pick an origin to evaluate at, which gives me, when I add this to c, I get something even, and a natural candidate for that is c itself, since if I add a vector to itself, I get back to something even. Minus c would also work. So there's not a uniquely defined Fourier transform. There's a choice that needs to be made here. But basically what I've done now is I've taken away the coordinate x, and I've replaced it by k, except that, of course, I should put in the exponential term. And for some reason, I have a minus sign there. Okay, so more explicitly what this is, if you want to write it down in a way that you can evaluate it, is that. Okay, and what this is simply taking, taking an orbit over all the translations and multiplying by the phase factor e to the ik. Okay. So now we can simply, so now you do some calculations. And you prove in a very straightforward way that the density matrix, when I Fourier transform it, satisfies the following equation. There's an I there. Okay, where, so it has a Hamiltonian part and a dissipative part coming from the Lindbladian as above. AK is a sum of, let's see here, a hopping term and a potential term. I guess I should put, now the V is okay because I used V. And the definition and the action of these operators is as follows. So, right, these guys, so what's happening here is I've replaced this space here as a direct integral over K of L2 of ZD times omega with the probability measure on omega and counting measure on ZD. And so the function psi, that's where that lives, is in that Hilbert space. So I take an element of that Hilbert space, I want to act on it with this generator LK, and if you do the computation, what you discover is that the Lindblad generator is transformed in the following way. So the Lindblad operator before simply induced hopping in eta. When you look at its action here, it gets mixed up with the translation of the disorder coordinate in the following way. Okay, so that's a computation that you simply sit down and do. And then the t, which comes from the nearest neighbor hopping term, has, again, the structure of mixing up translation of the disorder coordinate and the position coordinate you see. Okay, again, it's a computation that you simply do. The kinetic term, when acting on the variables x and c, does hopping in both x and c and when you work it out in the translations, you get exactly this representation. Okay, so, and then V, which comes from the random potential, is a multiplication operator. Well, not multiplication, sorry, multiplication with respect to a function of omega. Remember that we're always working here with the commutator with h, and that's where the differences here come from. Okay. It's not surprising that these things vanish, that this vanishes when c is equal to 0, because that's exactly vanishing of the diagonal matrix elements when I take the commutator with v. Okay, so you simply do this computation, and now we've reduced the problem before that we had before to a family of problems on these spaces L2 ZD times omega. The initial condition here, of course, is delta 0 c, and it was non-random. So let me just make that explicit by saying 1 of omega, which means it doesn't depend upon omega. Okay, but now we have to relate this back to the moment that we have written there, and so that's the second thing that one proves, which again is actually a straightforward calculation. So the moment that you want to compute, which is the sum over x of x1 squared, expectation value, this is actually equal to the second derivative with respect to k1. Okay, that looks like a decent way to pull down something like the up to some factors of 2 that I may have left out of my notes here. Right, the a that sits there corresponds to the 2a that sits in the first position of psi, and so I should have written this down. So okay, so this is the initial condition, delta 0, 1, that we started with. This I haven't defined. It's the semigroup which I'm using up there, and I should have written okay, and delta 0, 1 comes from wanting to evaluate this at c equals 0. That's the 0 here. 1 is the averaging with respect there. And so this is an identity that you then prove. And this uses, in a strong way, the shift invariance of the averaging. So the averaging here, where I average over omega, I can replace that by averaging over omega shifted by x. Okay. Okay, so now I've really reduced the problem to something where I just need an analysis of this operator. And I need to compute these derivatives. Okay, and of course, when I compute the derivatives, I get some integrals over time. Standard formula for differentiating a semigroup. And I have to take the second derivative. But things simplify a great deal. Because of the assumptions that I put on the invariant state for the Lindblad generator. Okay. In other words, actually, I should have evaluated all of this at k equals 0. So when I plug in k equals 0 here, this guy's both a left and a right eigenvector of this g. So g 0 delta 0 tensor 1 is 0, and also from the left. Which, in other words, the adjoint of g acting on that gives 0. Okay, and this is key. Okay, so this guy's always a left and right eigenvector of the 0, so it's clearly a left and right eigenvector here because I'm evaluating at c equals 0. So anything that lives at c equals 0 is annihilated by the potential. Here, when I plug in k equals 0 and I look at something that doesn't depend upon the random potential, this guy gives 0. So T0 vanishes on L2ZD tensor of the function that's constant on the disorder space. Okay, so this always holds for the random Schrodinger components, but it's an assumption that it holds for the Lindblad thing, which traces back to this assumption that I made about the invariant measure. This is always a left eigenvector for the Lindblad operator, but it's not always a right eigenvector. And actually, the problems with extending this to a more general thing come exactly from not knowing this right eigenvector. Okay. So when I do that, see, notice what happens when I take derivatives here with respect to k, and I write down the semigroup formula, I get a whole bunch of things, but wherever the semigroups, when I evaluate at k equals 0, are sitting next to this vector, they vanish. And so what we have here, so let's give this guy a name. Let's call this mt for moment. is a formula which relates MT to a particular vector. So it's there. Where phi, if you work it out, is the following, where E1 represents the first elementary basis vector in the first direction, which is coming from the fact that I'm differentiating with respect to that. Okay, so again, this is a computation that you do that's very straightforward. Okay? And so this obviously comes from differentiating the GK. It's coming from exactly this guy right there. Okay, so now one wants to estimate, one wants to analyze the long time limit of MT over T. And there's a nice thing we can do, which is use a Tauberian theorem. This holds if and only if the same thing where I put an exponential average. If this guy goes to D. Now as eta goes to 0. So I really have the necessary hypotheses, so I can basically replace this now by a problem about the resolvent of G0. So this is, so when you do the integral here, of course, the eta swallows up one of the exponential factors, the other one produces the resolvent. This is nothing other than phi 1 over eta plus G0. So now I've reduced it to a problem that there's some great hope of solving, because if there's one thing we know how to do, it's estimate resolvents, right? And so we can in particular do something like the Schur formula to reduce things to something nice, and in fact that is the next step. So G0 is a nice operator. It's the sum of these three parts that I wrote down. This guy is actually a self-adjoint operator. It's not entirely clear, maybe, that it is, but it is a self-adjoint operator on the Hilbert space that I'm looking at. L is non-self-adjoint. It's actually still the generator of a Markov process, well, at least at L0. It's a bit complicated because of this hopping in disorder. But the key thing that we need to know about it is that the real part of L is bigger than or equal to C, which was the constant that I wrote down before, times P0, I want P0 times the identity minus P0. And P0 is equal to projection onto C equals 0 in my Hilbert space. So when L hits something where with a delta function at C equals 0, it gives me 0. Okay, we already saw part of that here. But everywhere else, it's actually strictly dissipative. And that's the key thing. And so the rest of the calculation comes down to I see I'm not going to get to the localization part, but that's okay. I can explain it to anybody privately. So let me just finish the calculation. So G0 has the following structure in a block matrix form. First of all, we already have an eigenvector, delta 0, tensor 1. But fortunately, the thing we're looking at, not fortunately, it's by construction, is orthogonal to that eigenvector. Okay, and here, I'm just going to put that here. The real part of G01 is bigger than C on the corresponding subspace, which is exactly the range of I minus P naught. Now, P naught has two components. One is this thing corresponding to the eigenvector, and everything else. So everything else I'll put down here, and the coupling between this space and everything else actually comes from the kinetic term. So there is coupling. And I'll just call this T12 like this. I suppose these guys should be superscripts because the other one was a superscript. So the operator has this particular form. And this is really all we need to know. And the point is, so we have three subspaces. We have the span of the eigenvector, which is one-dimensional. We have H1, which is the range of this projection. And we have everything else, which actually is everything that is supported at c equals 0 and has mean 0 as a function of the disorder. So what lives down here are mean 0 functions of the disorder that are supported at c equals 0. And now we have to compute the resolvent. And in fact, looking back at the vector that we have, this vector phi lives in the subspace H1. So we just need the projection of the resolvent here, and so we end up with phi 1 over eta plus G01 plus u squared over eta T12 T21. Okay, and there's still a problem to be solved, which is what I'm going to finish with. Because, of course, this is a kind of a singular limit here. Eta is going to 0. This part's blowing up. But the end result is that, so this comes from the Schur formula, of course, and the end result of the computation is that I can take this limit and let's just phrase this abstractly. So if I have b, which is bigger than or equal to c, and I have a non-negative operator, and I look at the limit as lambda tends to infinity of the resolvent of b plus lambda a, and actually if you want to be careful, it's the weak operator topology limit, then this is actually equal to where pi, I want this guy to be normal, is equal to the projection onto the kernel. Okay, and this is a simple lemma that one can prove, that looking at a resolvent here, we basically just get the inverse of b restricted to the kernel of a. The point that because b is strictly dissipative, actually I don't need b, I just need the real part of b. Because b is strictly dissipative, this inverse exists just as well as the inverse of b on the corresponding subspace. And so this thing simply goes down to where I have to put projection onto the kernel of A here, but where A is this operator, but T21 phi is equal to 0 because T comes from the kinetic hopping term. The T21 is exactly this hopping between a particular subspace, and it's a complement generated by this at k equals 0. And this guy vanishes when k is equal to 0 on anything that's independent of the disorder, like this function. And so we get that. And so we don't actually have to worry about the projection, which is important because we want to prove that this is strictly positive, that we've actually evaluated the correct behavior. And so this converges to something, and we have an explicit formula for it, which is a positive number, which is finite. And so I guess I should just finish with what happens if there's no disorder, because that question came up at the beginning. If there's no disorder, then the formula I get here is actually much simpler. I just have exactly phi. So I don't need to worry if there's no disorder about the presence of the disorder coordinate. And in particular, this term is actually absent because I can never get up to the part of the space with the disorder coordinate. And I just simply get this. Sorry, 1 over eta plus g L naught. Wait, what happened to the g? Which converges to, right, when eta goes to 0 to this. And that's the 1 over g that I claimed at the beginning. Okay. Good. So if anybody's interested in the localization part of it, I'm happy to explain that to you in private.
Okay, well, thanks very much.
Let's leave.
Any questions or comments?
Two questions. So the first one would be, this is very, very general so far.
Yeah.
So for example, you can apply that to the quasi-periodic in one dimension and try to see what would be the difference between localization and delocalization regime. When the Lyapunov exponent is strictly positive, presumably you get C times G. But what happens when the Lyapunov exponent is equal to 0? Did you try to see?
I have.
What
You
kind
mean
of
still
scale?
localization, but power law?
So
That's
Spectral, we do not know too much.
Yeah,
That's true, but it's all hidden in the T1 to T1, right? I mean, this is
a good question, because what is the difference between ballistic or diffusive? Whether this quantity will fill.
well, this right. In this case, right, for ballistic you get 1 over g, and for
But
right, and for diffusive,
absolute continuous, but weak localization, roughly.
well then no, actually, you know that if the system behaves diffusively without the Lindblad generator, then the limit will simply be it will be continuous in the limit. So right, so the weak localization regime would be characterized by g of d of g converges to some d naught, which is positive.
So it's an interesting question in the model when we know there exists absolutely continuous spectrum like a Bethe lattice or quasi-periodic.
No, better lattice is better.
But
And
see, the Bethe lattice.
two regimes.
We have transport. You have a coordinate here. It will
Yeah, this is I'm not sure what to do with this on the Bethe lattice, because in the Bethe lattice, of course, you have ballistic transport.
Yeah,
And
and the space is quite straight.
exactly. So, and I don't have a Fourier transform like
But
this.
do you have a ballistic
I mean,
transform even in a regime outside the spectrum of a Laplacian when you have absolutely continuous spectrum in this Eisenman-Barzel regime?
I think so.
It is ballistic there too.
I believe so.
The resonance induced absolutely continuous spectrum is also ballistic.
I'm not 100%.
no, they don't. Actually, I think the resonances don't count for the transport. I mean, this resonant.
I don't know.
Outside,
Yeah, I don't know. I don't know. But this whole thing is really uses the Euclidean lattice, and right, the Fourier transform is also central to this. And I mean, okay, probably there's some sort of non-abelian Fourier transform of the Bethe lattice related to free groups, but
But you computed the expectation of the diffusion constant. What about fluctuations? Say variance.
that's a good
You
question.
have some, I know, hints what is going on.
No, I don't. I don't have hints. I mean, actually, this
It's
is
not
something.
zero, just zero, not zero. Fluctuations.
Right.
There should be, I believe. Yes.
So I don't have anything mathematical to say about that, and then whenever I try to think about it more heuristically, I can convince myself either that it should self-average or that it shouldn't, depending on how I look
Yeah,
at
but for
it.
that you have to.
And so,
There is another definition of the diffusion constant just by using Kubo formula, and there you can prove it self-average in principle.
In
Okay.
principle,
I don't
okay.
know, never tried, but
Uh-huh.
it means that it will be like for the conductivity. You
But
can.
how do you know that it's the same diffusion constant? In the sense that it's not the same
Yeah,
constant.
no,
I mean,
I-
so
I
I mean,
didn't feel it out.
right.
So
So,
I didn't
I
say
mean, if I had-
same. I said there is another definition.
If I had to
okay,
make-
yeah, for a
I
different
don't
level,
know.
which makes sense.
Yeah, if I had to make a guess, and you really, insisted to make a guess, I would I would shoot for self-averaging, so there are no fluctuations. But I don't have a good way to
The guess what is
prove it.
What is the guess once more?
Note that the fluctuations are 0. on this scale, because it's self-averaging. But that's purely based on the heuristics of, look, this is computed by looking at the wave packet traveling through many regions of space over a long period of time, and so fluctuations wash out. Yeah.
I also had a question. I mean, how realistic are the assumptions in your Lindblad? I mean,
Well, that is a good question.
You use them. I mean, they're heavily used in the proof, right? In various reductions, and to be able to analyze the operators.
So.
It depends on the model of environment, yeah?
Right.
Yes, exactly. Is there a model of environment where you can trace
like,
them down?
like boson bus, which everybody
If
takes?
we start with the Nelson model, with this translation invariant interaction, you would.
Yeah, but the thing is that if you really do the Van Hove limit, then you get this thing.
The
Is not
interaction
in
is
boson?
IKX.
Huh?
The interaction between is the coupling function is exponent I momentum k dot x, where x is the.
I see.
So in that case, it is translation invariant interaction.
Yeah, this is clear. No?
And then you should actually.
But if in computing the Lindblad you suppress the random potential and compute it just for the kinetic term.
That is correct.
So here's okay. If you want a Lindblad generator of the form that I have, do the following: couple the particle without random potential to a heat bath.
Okay.
Do the Van Hove limit, and take the infinite temperature limit, so beta equals 0.
But
Beta equals 0 gives you the symmetry that I need.
don't you have a problem with the boundedness of your Lindblad?
No. The Lindbladian in that case actually is bounded.
Okay.
Yeah. Because that just comes from the lattice. That it's you
Okay. Okay.
No.
Yeah,
It's,
sure. Okay. Okay.
it's not obviously doesn't look very bounded because it involves convolution with a delta function kernel and momentum space, but when you look at it,
the
it's actually
environment spin system, it is certainly bounded, but
Right.
is the boson bus, I'm not sure.
no, the Lindblad is bounded. The Hamiltonian for the boson bath.
To the boson creation and the annihilation.
So what you're saying is that actually the problem is that if you start right with a true coupling, then your Lindbladian should not be independent of the random.
It should be stochastic. It should depend upon the random potential, and it should.
Okay.
Yeah, right. So the thing that you get with the heat bath or the phonon bath, whatever, is something.
But you really need a Nelson model for this. You need a translation invariant coupling.
Yes, and then there's some detailed balance terms that sit in the front here.
Design.
But if you take the infinite temperature limit, these become
system
equal
and
to
the
one another.
interaction with environment would not necessarily be random.
That's correct. But you need in translation. The interaction, the field operators have to be translational invariant in order
Yes.
to get something like this.
But that's reasonable.
That's very reasonable. That's
Yeah.
exactly what you should do if you
Right.
want to get this.
But the trouble is that to get this, you need to suppress the random potential of the computation. So this really would make sense at small lambda,
Yeah.
but I want to use something at large lambda. Okay. Well, I still think it's a reasonable problem. Just so the other thing to think about, sort of heuristically, is that it's fairly reasonable to take this limit where the thing simply mixes all momenta equally, because locally, because of the random potential, you've sort of broken all the symmetries you might make. And it wouldn't certainly make sense necessarily to consider detailed balance at some temperature for the kinetic term alone. Okay, so, but that's a little bit.
Actually, I think that's the problem we looked in Minneapolis in 1994. That one should really look back to the original jump process on the
Yeah.
energy levels and try to understand it.
I mean, it's not hopeless to understand it.
I think we postponed this
Yeah.
for private discussions, and it's already turning.
All right, thanks.
Yeah. Okay. Thanks very much, Jeff. And
Yeah, thank you.
at 2, but instead of the room.